So from here, we have a series of reactions that we look at for each of these functional groups. And the first of these reactions is hydrolysis. So hydrolysis is going to largely be the opposite of what we saw in the last video. So our previous video talked about how we convert carboxylic acids into a number of different functional groups. In a hydrolysis reaction, we're going to add water, and we're going to form carboxylic acids. So again, it's essentially the opposite of what we just saw. Now, this reaction is most important for esters and amides. We'll look at it for the other two functional groups, acid chlorides and anhydrides, but it's not nearly as important there. And the reason it's not as important for those is because usually if we're going to have an acid chloride or an anhydride, it's because we've made them from a carboxylic acid. And so it's not very common that we would then want to take that and immediately go back the other direction. Now, that being said, there certainly are cases where it's useful to turn one of those functional groups into an acid, and so that's what we'll look at here. So in the case of the acid chloride, all we need to add is water. We don't need to activate the carbonyl. We don't need a better nucleophile. And that's because the acid chloride is such a good electrophile that by itself, water is a sufficiently good nucleophile. And so the water will attack the carbonyl, push the electrons up onto oxygen. And that forms our tetrahedral intermediate, which we've referred to quite a number of times in this section. Here, the O- adds its electrons back in, kicks out the chlorine, and we have what is essentially now a protonated carboxylic acid, which by losing a proton gets us to our product. For anhydrides, we're going to see in a moment that the story is largely the same. Realistically, the only real difference between the acid chloride and the anhydride reactions is the identity of the leaving group. But once again, as with acid chlorides, the anhydride is a sufficiently reactive carbonyl, a sufficiently good electrophile, that water can attack without any activation. So as we said, the reaction here for the anhydride is exactly the same. Water attacks, we form our tetrahedral intermediate. The tetrahedral intermediate breaks back down, kicking out our leaving group, giving us our protonated carboxylic acid again, which loses a proton to give us the product. Now for esters, this is a much more important reaction, the idea of hydrolysis. And for esters, esters not being nearly as reactive as anhydrides or acid chlorides, we do need to do something to make it more reactive. And so we have two options. We can use acidic conditions, which is going to activate our carbonyl, or we can use basic conditions, which will give us a stronger nucleophile. Now, typically base is preferred because it gives us better equilibrium control, but we will look at both sets of conditions. And so we'll start with the acidic conditions. Now, you should recognize as we go through this mechanism that these steps should look very, very familiar to us. And the first step, under acidic conditions, we know that a carbonyl will protonate. That's what activates it for nucleophilic attack. And we needed to activate it in this case because we have a weak nucleophile, which is water. Upon doing that, that's where we get our tetrahedral intermediate. We get a proton transfer from one oxygen up to the oxygen that was on the ester. That makes our R group over there a good leaving group. The OH can add in its lone pair, kicks out methanol. And loss of a proton gives us our product. So when I say this mechanism should look familiar to us, the question is why? And the question is, what does it resemble? And so if you think back to our reactions of carboxylic acids and the Fischer esterification, what was the mechanism for a Fischer esterification? In that reaction, the carboxylic acid was our starting material. We activated it by protonating it. Methanol attacked, or whatever our alcohol was attacked to give us a tetrahedral intermediate. We transferred a proton. We kicked out water to give us the carbonyl and lost a proton to get the ester. So in other words, it is the exact reverse of the Fischer esterification. Now, of course, that does complicate the reaction because that means in this reaction we're always dealing with an equilibrium situation. And so we always have to take into account, whether our reaction conditions that we use, are they going to favor the acid or will they favor the ester? And so because of this, in general, for ester hydrolysis, we prefer basic conditions. Although, as you'll see, basic conditions do have their own issues as well. But the typical hydrolysis, the most common way to hydrolyze an ester, is using hydroxide. Now, with hydroxide, because hydroxide is a stronger nucleophile, in this case, we don't need to activate the carbonyl. Remember, we've said in a number of cases that that's our option. We either get a better we get a better nucleophile, or we activate the electrophile. Here we've chosen a better nucleophile, so hydroxide attacks, we form our tetrahedral intermediate. At this point, O- adds back in and kicks out the methoxy group to give us our carboxylic acid. Now, at this point, in a lot of ways, it looks like our reaction is done because we have the product that we want. But this second step here, where the tetrahedral intermediate breaks down, is actually not very favorable. And the reason it's not favorable is we have, this poor leaving group here. We've said in the past that things like, OR minus make for poor leaving groups. The issue here, though, is if any of it leaves, even if the equilibrium is pretty terrible. we end up with a good acid, our carboxylic acid, and a strong base, OR minus. And so they'll undergo, what seems like a very simple acid-base reaction. But it's this acid-base reaction that is the entire reason this reaction goes forward. If you think about a typical carboxylic acid, pKa, is somewhere around 4 to 5. But an alcohol has a pKa much closer to 18. So we have a huge preference in favor of, the forward step here. And so because there's such a strong preference in this reaction, this step to go forward, this is the entire step that drives the equilibrium forward. Finally, at this point, once this has happened, we quench the reaction with acid and we get our carboxylic acid back. Now, where might we see a reaction like this? Well, the answer is a lot of places, but maybe one of the best examples, and it turns out that this is such an important and common example that sometimes you actually see basic hydrolysis of an ester referred to as saponification. In saponification, which stands for soap making, if we start with a triglyceride, which actually has 3 esters, as long as we add sufficient hydroxide, we can cleave all 3 of these esters. And as a result, we get these carboxylate salts. These are all of our soap molecules. So this is how you make soap. And as a byproduct, also a useful molecule, we form glycerol. And glycerol is used in skincare products, or you can put nitro groups on those oxygens and form nitroglycerin, which is used in gunpowder as well as a vasodilator. All right, our final functional group to look at hydrolysis for are amides. And with amides, we almost always use acidic conditions. Why acidic conditions? Well, in the case of an amide, if we use basic conditions, that would require us having something like Nr minus or NH2 minus as a leaving group. And as bad a leaving group as OR minus might be, a negatively charged amine leaving is even worse. So mechanistically, we're going to do it with an NH2 group here, but it wouldn't matter if this was NH2 or nitrogen with a couple of R groups. Again, we do this under acidic conditions with water. As we've seen many times before, the carbonyl protonates. This allows for our weaker nucleophile water to attack. Giving us our tetrahedral intermediate that we've seen so many times before. We now get a proton transfer from this positively charged oxygen to the nitrogen. That's turned the nitrogen into a good leaving group, which the lone pair on oxygen will help to drive out. This step is typically irreversible because the leaving group here is NH3, or ammonia. And ammonia, as long as we're not at low temperature, which we're not going to be for this reaction, will be a gas and will just evaporate away. Finally, that positively charged oxygen loses its proton and we get our product.